Hello, today we are going to take a closer look how to convert a Gordak handpiece to a Pace MBT soldering station, and how can you design the circuit board, how does it work, what kind of drawbacks you have. We are going to compare the two handpieces, talk about the theoretical part, the schematic, the Arduino software, the code, and at the end of the video we are going to test it out, our handpiece converted to be usable with the Pace MBT station. So these are the topics for today. Let's get started. So why would anybody want to use a Gordak handpiece with a Pace station? Well, there can be multiple opinions about this, but the first and the biggest one is I have laying around all the necessary components and tools to make such a conversion. It can be done quite fast, quite easily, and the Pace handpieces, the original ones, are quite expensive, over $150 each. I think without the tip, the soldering tip. They have quite a long lead time also, and yep, as a weekend project, a one-day project, this was a perfect one. And now let's see a few differences between the Pace PS90 and the Gordak 936 type handpiece. So they both work from 24 volts AC. Their maximum operating temperature is, for both of them, 475 degrees Celsius. They both last for over 5 years. This one, the Gordak, that lasts more than 5 years, I can tell you from my own experience, since I'm using this old one more than 5, maybe 6 years is going to be this year that I'm using it. For a long period it was used on a daily basis, more than 3 to 5 hours a day, and I had worked it a lot. So for their price you can get quite a good quality, and for most of the daily soldering tasks it's more than enough. Well, the power output of both of these handpieces is around 50 watts. Well, 50 watts, you think then both of the handpieces are quite good? No, they are not. I'm not trying to fool anyone here. A Gordak handpiece is less good than a Pace one. The Pace one is made for multi-layer, huge ground plane boards. These ones, the Gordak ones, are made mainly for two-sided PCBs and not that industrial kind of soldering. And so, as I mentioned, the Pace is an expensive handpiece, the Gordak one is a cheap one. You can get a simple handpiece for around $2 or $3, but I never had to replace mine, not even the filament. And the other major difference is that the tip temperature, the measurement of the tip temperature is made by, in the case of the Gordak, by a K-type thermocouple, and by the Pace with a PTC, a positive temperature coefficient resistor. So it's very different. You cannot just hook up a simple Gordak handpiece without any kind of modifications to a Pace station, because a thermocouple outputs a voltage, an active value that can be measured, and a resistor, a resistance of something is a passive measurement, a passive value, and this one spits around in the around 10 or 20 millivolts, and this value varies between 100 and 300 ohms. So they are completely different. But the filament, what's inside of them, they are exactly the same. So how can then we fool a Pace soldering station to think that we have connected an original Pace handpiece to it? Well, a few years back I managed to see how these stations are calibrated and how they are controlled. They are so-called C1 and C2 calibrators. What can you easily stick inside the connector of the soldering station, and the PTC, the value of the resistor in the tip of the Pace. So the resistance varies between 100 and 274 ohms. 100 ohm at around 200 degrees Celsius and 274, 75, 76 ohms for 482 degrees Celsius, which is the maximum output temperature of the station. So how can we do this? Let's see it. We can convert the K-type thermocouple to a PTC in two ways. One is easier and one is harder. One takes more time, the other one takes less. The first one, the harder one, is about converting that output voltage to a resistance by an analog circuit, but the calibration of that circuit is a long job, and it's going to take time. You also have to modify the circuit board of the Pace solder station. Maybe I forgot to tell in the beginning, I don't want to make major modifications to this station. Later I'm going to get some original Pace handpieces, and I want the station to be as clean, as original as it can be. So the analog method is not suitable. So we have only one way. We can pick the digital one. So what we should do? We need to read the temperature of the thermocouple, and based on that temperature we have to simulate a resistance, what can be measured by the station. But what kind of electronically, digitally controllable resistors we know, or we can buy, or find, or make, or get, or steal? So the three basic ones are the electromechanical. Maybe if you have opened old HiFi stations and on the volume knob you have a motor, and on the same shuffle you have connected a potentiometer, so as the motor gets a command to turn to the left and to the right, the output volume decreases or increases. But these kind of resistors together with motors nowadays are hard to find. So this is not going to be our solution. By the way, you can also make some kind of assemblies with some servo motors and classical potentiometers, but that's a hustle in plus, and that takes a long time, so it gets even more complicated. We can use digital potentiometers, which could be quite a good solution, but I don't have laying around 100 ohm digital potentiometers, only 1K ones, and I don't want to wait till I get one, since also the lead time is long. So the digital potentiometer is not a solution. And I picked the last one, the discrete component potentiometer. And how can you make one? We are going to talk about it just now. So this is the schematic of a digitally controllable resistor network potentiometer, or you can call as you want it. As on the previous slides, I showed you that we have a maximum resistance of the tip of the base tip of 275 ohms at around 480 degrees Celsius. So we need to create a resistor network, all of them connected in series, and step by step every resistor, as the temperature increases, is going to short both the resistors in series to the ground. So if we have 200 ohms, then we are going to short to the ground here, so in this path. And this way the Pace thinks that the temperature of the tip has changed. After that, as our handpiece is getting hotter, we are going to turn this transistor off and turn this on. Since that the resistance increased by 10 ohms, 200 with 10, 210 ohms, so the temperature of the tip has increased, and we can make these kind of networks to an infinite number practically. You just have to enough output pins of your microcontrollers and enough transistors to switch between them. And as you see, one side is going to be always a ground, and the other one, which enters the Pace station to the op-amp, that amplifier network, is going to be always the positive. And my idea was to control these and MOSFETs, these transistors, by the output pins of an Arduino Nano. And the same Arduino Nano is going to measure the tip temperature of the Gordak handpiece. Another converter board is going to spit out a digital data about the temperature of the tip. And all the other tasks are going to be, all the other decisions, when to turn off the heater and when to turn on the heater, is going to be decided by the Pace station, rework station. So the Arduino code is very simple. You have just a while loop, the main loop, which runs infinitely, like one while in a while loop 1 equals 1, which runs infinitely. You have to compare the temperature to predefined values, and when you got your value, your desired value, you turn on step by step of these transistors. And when the tip reached the maximum temperature, then you close all of them. Like close, it's a bad expression. You pull them all gates of the transistors to the ground. So turn them off. And that's about the theoretical part. Now let's see what have we made. If something was unclear, don't hesitate to drop a comment or to notify me in some kind of ways. I can offer both the schematic and the code if needed by anyone. So here we can see the whole assembly, the Pace solder station on the left side. In my right hand, the soldering iron, the Gordak soldering iron. Here we have just a plug, because I did not want to cut the Gordak's original cable, because it would be a shame. You can pick up these kind of DC plugs. I managed to find this plug at a local reseller, local Chinese, mostly Chinese reseller, which fits perfectly. It has quite nice solderable pins on what I can solder the cables. Here we see the prototyped electronics with the 7 and MOSFETs, with the Arduino, with the K-type thermocouple amplifier circuit. And if we try to turn it around, you can see the bottom side. On this part of the circuit, maybe with a, you can see on this part of the circuit we have the voltage dividers, and these MOSFETs are used to short them in sequence according to the tip temperature. And that's how we managed to fool the solder station to think that it has a real handpiece in it. After successfully managing to prototype the circuit that converts the handpiece to be suitable for the Pace solder station, now let's try to make some solder joints and see how it performs. So we have just a perf board with some salvaged components, some transistor, a buzzer, smaller and bigger capacitors, some even bigger capacitor, that inductor, and a few more capacitors. On the other side, if we zoom on just a little bit, we can see quite well how we are going to solder. So it's a bit hard for me to solder since I'm looking at the phone screen. And the board is not in the best shape. That one. And that one. And maybe this one. And if you take out this transistor to hold it more stable the whole board. We can make a few more joints. There. Some other there. And maybe this one. And the last one in this example, and just fall out. Let's try maybe this one. All right, let's check the solderings. They are quite good in my opinion. Not the best, but we have to keep in mind that these kind of perf boards can oxidate quite easily, and sometimes they are quite hard to solder, since if the tip of the soldering iron is too hot, then you are going to take off these small pads, since it's a bad quality PCB fur board. So you have to somehow balance. Or you can clean the boards to take off the oxide layer on the copper. But as you can see, you can solder quite well with this iron at around 420 degrees Celsius. They are okay. Now let's try to see how well we can wet some pads, but cleaning them a bit before trying to solder, to make the soldering just a little bit easier. Like here. So it sticks for the first time. It sticks for the second time. Probably also for the third time. Yep. We can try even to remove some solder with a bit of solder wick, which also helps to see how well an iron performs. And that's it. And also the third one. I think it's okay. And sometimes I make a test of trying to solder a coin, since a copper plated coin has quite a big thermal mass, and this puts to a quite hard test the soldering iron, how fast it can pump energy, heat into the coin. Just clean a little bit to take off the oxide layer, and again It is recommended to put just a little bit of flux to help the solder, to make the contact better. Something like this quantity is maybe quite enough. I'm sorry for the movement of the camera. And that's it. And now put it on some surface, just not to burn my table, and just try to solder it. Just a little bit more solder. A bit more. And as you can see, oh, my recommendation is to always use a fume extractor, but I don't really have right now. And you see, the coin is getting soldered quite fast, and this iron is quite usable with this transformation, so I consider this project as a successful one. Yep, right that. And it's soldered completely. I believe I managed to do this in less than a minute.